friends, online friends. Welcome back for another BrIAS Seminar. Also for those of you who have not come here, so welcome also to the location of FARI, where it is joined with the institute like BrIAS. And so we have at heart to try to highlight the expertise within the two universities and through BrIAS to really connect, extend our knowledge. Connections also on the topic that we had chosen for this year for sustainable robotics. So to kickstart today, we have the honor of having Professor Bernardo Innocenti. He's at BEAMS, Bioelectro and Mechanical Systems at Polytech Brussels, the engineering school, and he will be talking about evidence in innovation in the field of orthopedic. I'm looking forward to hear what you have to say. Thank you.
Thank you a lot. So ladies and gentlemen, physically and virtually, good afternoon. So I need to talk about innovation in a field that I'm working since 20 years, is orthopedics. And I will need to highlight that I have some disclosure to make, but the presentation that I'm going to do was not altered due to the fact that I interacting with different partners in the field. But before starting to talk about the subject, I want to, and thank you for the nice presentation. So, okay, I'm Professor of Biomechanics at the Polytechnic School since 2012. I'm also guest professor in K11. And since the beginning, my main research field is orthopedic biomechanics. No worries, I will explain what does it mean. And I work mainly on the human knee joint. I think you know what is a knee. And I will try to give some example on how we can deal if we have a problem, and also how we can help the people that want to solve this kind of problem. My career was always hybrid between academic, hospital, and industry. And I always think that only we work together, we can do the stuff better. And I was also active. I am the founder of the CAOS Belgium. The CAOS is a computer-assisted orthopedic surgery society. It's an international society. And we also do the Belgium session in 2015. Now I'm vice president. I'm also a member of some society in the clinical side, in the biomechanical side, and so on. So the main topics today is to talk about innovation and how we can, as engineers, improve this field that is extremely multifactorial. And I will explain what should be the path that bring innovation in the field. But we need to pay attention to one thing that is quite important. The aim of the game is to make the life of the surgeon better, but in reality, what at the end we want to do is to make the patient happy. And if I want to follow the journey, the trip that a common patient have, we need to consider three different periods, because we have the initial period, the pre-operative period before the surgery, and we need to help the surgeon to give some tools and tricks to make this better, not to make mistakes, to clearly identify as soon as possible the eventual treatment and how to provide this treatment. And also we have, in some cases, the real treatment, so the intra-operatively, where we need to open our joint, see what happened, and do what is necessary. But it's not finished yet, because after we need to see what we did is okay or not. We need to follow if we can improve, if we really are able to judge the quality. And this is quite important, because if I want to analyze something, we need to go from something that is going less and less qualitative, yes, it seems okay, to something that is quantitative. I have a number, I can judge and I can measure. And all these numbers, all these tools, and this is something that I would like to stress, and I'm on slide 3, is the concept of trust. I mean, if I have a patient and I want to use a tool, I need to trust the tool. The surgeon needs to trust in a certain way what he's using. The patient needs to trust the surgeon that is using the tool, and so on. And so, given this evidence and trust, I will hope to give you some nice take-home message at the end. So let's start. I think that today, if we open newspaper electronically or physically, if we watch TV, we are submerged by a lot of work, and most of them are artificial intelligence, robotics, 3D printing, big data analysis, and virtual augmented reality. These are some of the main innovations that enter in the field and enter our society, enter our interaction between people working and so on. And honestly, this change our daily task. In the past, if I want to go from one place to the other, I take a map. After I buy a navigation system, now I use a watch. And I want to do the same, but it changed the interaction. But this is also true in changing the work. The way that we work today is not the same that we work in the past. And sometimes we need also to think that also how the company will use this, maybe we will also change how we deal with the workers. If you see a picture on the beginning of the last century, we see a lot of people, now we see a lot of robots. And maybe the people are placed in other positions. And so these technologies enter our profession as an engineer, as a teacher also, very fast. And if you look also from some social study, they easily, clearly demonstrate and show that the way that we are working today is not the way that we were working 5 years ago, and maybe will not be the way that we will work in 5 years. And to give you a simple example now, as I just mentioned, I was responsible of the Belgian chapter of the CAOS. But we want to use this device in a better way, and the best way to use this is also to be able to make measurement, and in fact we are thinking also to add not only the computer, but also add sensors, add parameters that we can use to give numbers, and we can use this number and manage this number to obtain a better result. But I'm talking about biomechanics and orthopedics, and I know that are not something that everybody's working every day. So what is biomechanics? I mean, biomechanics is very easy. Already the word itself explains what does it mean. It comes from the ancient Greek, bios, life, mechanica, mechanics. So is the application of the mechanics to something that is alive. Usually it's a human, but we can also make study on animal, plants, cell, and so on. And we can apply the mechanics to the human beings in general because we are a mechanism. We are a mechanism. We have some joint that are some link, and also we have some muscle that apply some force to this bone. So we can say that the human being, it's a musculoskeletal system. As you can see, we are muscle that apply the force, a skeleton that moves. So when we do any activity and we see only our skin that moves, you need to consider that inside we are some bone that they are moving each other, and this bone moves because we apply the force that is generated by this muscle. And we can do a lot of things. We have a huge performance. Our friction coefficient is really low. We can play piano at 95 years. There is no any mechanical device that can do what we are able to do. But we need also to be honest that sometimes we have a problem. Sometimes we have a problem. For instance, we have our joint from the left that go to the right. That means some degradation of material, some pain, some limitation of the motion. And so we need to call special people, call it surgeon, orthopedic surgeon, because orthopedic surgery, is a medical specialty that focuses on injuries and diseases of the musculoskeletal system. So our knee that moves, to give you an example, and move because we have muscle, you see, have some problem. We need to remove the part that have problem, and we need to add some medical device, call it prosthesis, that replace the joint to have the same motion as before, as close as possible with the previous. But I want to start already to see what is the future of orthopedic surgery. And I want to go already to something that is really important. A very new paper that exists is the article, The Future of Orthopedic Surgery, 1948. So this is an article written by, at that time, the president of the American Society of Surgeons that was dealing about the innovation and the future. And you have a very difficult task, because if you read, you see, hey, guys, you need to understand that already what it's done, it's fantastic, because consider that we have already a lot of innovation. Because in 1895, we have the X-ray. X-ray is something that still today, everybody go to the hospital, you have it. And was invented in 1895. And pay attention, because he wrote something very nice to read, that this unbelievable changing life technique like X-ray, at the beginning, the use of this diagnostic agent grows slowly. So it was so important that nobody believed it. And now it's common, and they have it. But in the age that you see, the big problem was, for instance, in 1894, we don't even know what it means, orthopedics. And so we go from orthopedic to orthopedic surgery. And at that time, only in 1913, two surgeons from US, Gall and Robertson, start to do and present their study on repair of bone. Repair of bone is what is today is called traumatology. So if you fall, you break a bone, you know how to do it. But this is because there was something started in 1913. And the very big assumption you can consider for an hospital, there was at the beginning of the century, in reality in 1930, let's say, we have the big advantage of inventing the idea of aseptic surgery. So you don't have any problem on bacteria. Things of today, what does it mean have or not have a bacteria in an hospital? And so he was quite guessing, because can you imagine, all of this important stuff are done, but he still say, I see a lot of improvement in that. Because medical field is something, together, honestly, with engineers, that grow every time. And now we need to ask ourselves what we can do now. Because some years passed, 8 years almost passed from this article. And if you want to see what you can find, for instance, in knee prosthesis, you find everything. You can find different material, different shape, different function, and again, similar for hip. I want to highlight that I put hip and knees as example because they cover almost 90% of the implant. It's fine. That are so today. But for us, for an engineer, for a person that is interested to improve, I want to do a step back, and I want to say that any orthopedic device, like any device, is designed because I follow a certain philosophy and a certain approach. And to check if it's working well, I need to check how it works. So what is called performance in a certain patient. And I need to understand that the device alone, it's not enough to judge its performance, because it depends also how I position it, what is the orientation, the way that I'm using to put it, because if I remove everything, maybe it doesn't work anymore. If I have the right tools, because if I need to screw, I don't have a screwdriver, I cannot do. And can you imagine something that I need to open and close and suture? And also, don't forget that, as I mentioned since the beginning, we are a musculoskeletal system. So it's true that orthopedics is based mainly on looking bone with radiograph, but bone alone are not enough. We have all the soft tissue, we have the muscle, we have the tendon, we have the ligament, and they need to work, because they are the guy that are responsible to apply the force. And we move because we apply force. And in fact, if you keep a skeleton and you stand up, it will fall. The skeleton itself is not able to stand up. We need to have the force applied by the muscle and the tendon to allow also me to be stand up. And what I want to say is that to check the success, I need to introduce what is called a pyramid of success. So how we are able to make something well and good. So what we have at the beginning of the pyramid, we have the patient. The patient is our main focus. However, it's true that after the patient, we have the surgeon. The surgeon that sees the patient, the surgeon can see what he can do, and he tries to do what is the best for him. So just after the surgeon, we have the implant. Implant chosen by the surgeon looking to the pathology of the patient. However, as I told you, the implant alone, for all these reasons, is not enough. Because maybe you need also to put in the right position. Think about that you have a circle. If you clamp in the center of the circle, it will start to rotate. But if you clamp in another point, the circle will become a cam. And so you don't have the good performance, even if you have the right circle. So how we can do this? What you will have just after the implant? The surgical technique, how I can do it. That is nothing if we don't have the right tools. And so the base of this is the tools. What we gave to the surgeon are the base to make everything good. Obviously, it's normal that we have an influence from the patient to the tools, but it's also true that the tools influence the surgical technique. Only some two implants can be used, and also how the surgeon is able to put an implant. Don't forget that learning curve, it's extremely important. So we have surgeons that always put the same implant is able to do better than a surgeon that put the right time. And when we change the tools, we need to train this, and these also have an effect. Sorry. But this pyramid, you see there is some space between that. And to make a real pyramid, what we need to use, like the builder, we need to use the right material, the right cement, to glue all this part. And what is this cement? Is the trust. If there is no trust, for instance, between the patient and the surgeon, we will not have success. If the patient don't trust the implant, don't trust the tools that he used, there will be no success. And most of the difficult part is not to create, to generate, and to provide the right implant or tools, but to make trust on this. And to make the person use and trust what you need to do. But this is normal for you. I think that as an engineer, we use a calculator. Who uses a calculator here? It's easy. We push a button and we trust. Who try to verify by hand the result of the calculator? I never do it, honestly. And this is the real problem. Because we trust, and as soon as we lose this trust, we are out. And only if we have this trust in the tool that we used, we can move forward and we can do stuff better. And so if we have this, we can start to design, considering that the design also follows a certain evolution. Evolution because we can parameterize each of the parameters that we have of everything. I use a car because I think it's something that everybody knows. On the right, we have a knee prosthesis. Maybe it's not something that you see every day. But we can define this parameter, and we can optimize all of this, thinking that this design evolution in reality is extremely multifactorial. I give you a very simple example of one parameter that strongly influences the design, that is the time. Time, yes, time has changed, because the same car, in terms of time, changed the design, but it's the same car. The function is the same. And honestly speaking, you cannot sell today the car, maybe for some aesthetic reason, yes, but not for the same function of what you have at the beginning. And this is true also and especially in the medical field. What you will see here, it's a very old surgical theater in wood, with the light provided by the candle or by big window. Big window also help the ventilation because we don't have some problem with the bacteria. They are surrounded by people because most of the time we have people that want to see, as you can see. Can you imagine the problem of bacterial adhesion there? There is no mask, no gloves, nothing, because at the time we don't think there was a problem. And after we need to clean because it's in wood. And also this change because we start to understand that we can do stuff better. We can do stuff better in terms of space, in terms of material, in terms of all the various parameters. And now you see that you go from a very crowded region to something more aseptic, and also something more focused. But pay attention, something very important. You remember the top of the pyramid is a patient, and the patient is always in the center of the room. That is a guy. Even if we are the engineer that should provide the tool to the patient, to the surgeon, that will put to the patient. I think that usually, unless we are very young or we have a very strong wife, we bought our clothes by ourselves. We go in the shop and we go our shoes, our dress, and so on. In the surgical field is a surgeon that decides which prosthesis you will use. And it's us as engineer that we need to tell we should be the best approach and all the parameters that are behind to be able to decide the best device for the single patient. And now we are going to something very close to this. Because at the end, we don't need to make the surgeon happy. We need to make the patient happy. And so it's very important to understand that each patient has a different target and a different aim. And I want to give you, again, a very nice example that I found online, again with car. So if I consider three main persons, this comes from US, you will see from the image. So we have Alejandro that wants to go fast and have fun, and he has a target for his car, something like that. But we also can have Marge that wants to be safe and comfortable, and we have a car that is different from that. But it's different from that because the aim and the target is different. And you cannot miss Dale that wants to have big load and be reliable, and he wants another one. Three cars. And if you want to provide the car, the big mistake is to make a car that is able to make everybody happy. Because when you will start to sell something like this, you know the story, nobody will be happy. Because at the end, what is extremely important is to reach the target, and everybody have his own target. And I tell you the story, still we are discussing today if we can reach a consensus. Why? First of all, look around on your left and go on your right. Do it. You see different things. We are all person, but we are all different. We are all different in terms of anatomy. Today we also use a complicated word like morphotype. So we have the ectomorph, endomorph, mesomorph that represent a sort of proportion between our dimension. And also the same person became older. Unfortunately, you have, from a mechanical point of view, some problem because you increase the stiffness of your muscle, you increase your coefficient of friction, your resistance of your bone is lower, the lifestyle also change. That means that if you look to the left or you look to the right, we are all human, but all of us, we have different needs. We have different targets, and we need to pay very attention because we need to have different strategy to be able to make all of them correct. But also, we need to understand that even if I define, okay, I have this guy, what will be the target? Because we can optimize only if we know what we need to optimize. And sometimes we want to analyze my motion. Sometimes I want to analyze my force in the joint, in the knee. I want to have the soft tissue. But what I want to do, and this is the most important question that we need to be able to answer. And unfortunately, not everybody asks this question to the patient. Because the patient, he will go to the doctor mainly because he has pain and is not able to walk. But after the surgery, the patient go back to the surgeon, and the doctor will ask, do you feel pain? No. Are you able to walk? Yes. So you are happy? No. And that is a problem. Why? Because the patient, and this was something that was found several years ago, The patient wants to do stuff that sometimes with the prosthesis you're not able to do. He gave a sort of limitation. And it's impossible to make a device that is able to gardening, cycling, watch TV, go outside with the kid, play soccer, play tennis. But this is what the patient wants to do. And we need to be able to understand that are what we need to aim, and this is extremely important because we can have different activity, and we are all different. And so we have people that want to go to the gym, people that want to play soccer with a friend, people that want to be on the couch and watch TV. And from a mechanical system, the forces are different, the movements are different. We need to define a device that are able to accomplish this. And there is a last thing that is also my friend on psychology can sell this. If I look at a patient in the 16, the 18, 2000, and yesterday, we see the profile of the patient is changing. First of all, we abuse our joint, so we have problem earlier, and so the patient is younger. It's not a big deal because the company sell more prostheses, they're happy. But what is also true that with the same age, now the patient wants to do more. It's very more active. It's quite common to have people that do sport even at 60 and 70. But what is even worse, or it's even nice, is that the patient now have huge high expectation. He claims that with the new device, he gain also years. So I scream 2 years. I want to have 5 years back of my life. That is the approach. I remember when I was okay, it was some years ago, and I didn't really consider that a lot of issues change. So, and as engineer, what we can provide, I mean, we cannot change a patient. We cannot change a surgeon. We try sometimes, but it doesn't work. What is true, we start from implant, technique, and tools. And obviously, I want to show you that usually we start from the tools, and after we go and increase. Always, again, providing not only tools, but trust on what we're using. And how we can trust, how we can evaluate. I need to use, unfortunately, the center-solar curve in the claim that if you cannot measure it, you cannot improve it. So the most important things that we are trying to do, especially us and also other researchers in the world, is always try to do the step from qualitative to quantitative. Consider that up to, let's be honest, 15 years ago, not more, surgeon look at X-ray and say, walk, yeah, it seems okay. I don't understand why you have a problem. Because there was no really a measurement that you can do to link to a single patient to make sort of evolution. It was 20s, 30, now it's improved. Now we are going to introduce sensor, device, and so on to give number that could be used to see absolutely if something goes wrong, but not forget also if something doesn't go wrong. Because as engineer, we need to be honest that we grow by mistake. And we learn our lesson because we fall, we stand up, and we try to walk again. That is also how we walk. I mean, I start to walk, I fall, I stand up, and I will walk. Without making mistake, we don't do nothing. And the only way to improve is making mistake, and the only way to make mistake is to do something. It's true, if you don't do nothing, you don't make mistake. So, and if I want to talk about this, we need to see, as I explain you, the patient journey. So we have a patient, and he have a different level of interaction. That means the beginning, we have all the problem of the diagnosis. I have a problem, I go to the doctor, I want to see what happened, and I want to know why I have this problem, is what are called pre-operatively. Sometimes it's easy solvable, sometimes not, and sometimes we need to go so intra-operatively to give a certain treatment. And as I already explained you since the beginning, is not the end, because the end is also to follow the rehabilitation, the follow-up, the evaluation, with what is called post-operatively, with, again, the global idea of the optimal follow-up, and so we have an happy patient. And below all of this, we can put a lot of topics, I will highlight them, I cannot mention everything, that really show what we can do today and what are the technology that we are using to do this better. So the first thing is, for instance, an analysis on using modeling and dynamic imagining to analyze, for instance, this is a study that were done with a group of Professor Nico Verdonschot in Holland. The story is that I want to see if I'm able, with a single analysis, to check if I have my problem on my knee. Consider that the knee is made by the femur that is touching the tibia, but in front we have a small bone called the patellar that I want to tell you a story. If you consider 100 study on the knee, 90 consider only the tibiofemoral. If you have a problem on the knee, 90% of the time is problem of the patellar. So it's floating in the middle, and what we can start to do is to make a very simple dynamic MRI. So you can see, you do a flexion with your knee in the MRI machine, and we have a software that automatically, using artificial intelligence, and this is Professor Nico Verdonschot that was the first guy that do this test. Yeah, it's okay. And you can already, almost in real time, the pattern of your patient. But okay, this we can do, it's a nice game. But what is even nice is that we start to go from, it seems nice, qualitative, okay, I have a good flexion, it seems that the motion is okay, to a database collected by healthy people, and automatically you can track the motion of the entire bone to see if you have some discrepancy with respect to the normal population, that are the blue curve, with respect to the green, and we have a system that can help the surgeon to see this is a problem, this could be the treatment, this is what you should do, or these are the other exams. And this is really important because with one exam you already have a map of what you can do, reducing also the social cost, addressing immediately what you want to do. And obviously this is a part of the big study that we also want to evaluate the entire full knee motion, also considering tibiofemoral and patellofemoral contact, cartilage degeneration, and so on, because obviously prevention is extremely important to avoid the needs of a different treatment that sometimes is more aggressive. But what you see on the right, what you see before, what is really true is a guy that was flexing inside the MRI. What we used to evaluate what can happen is what we know is called modeling. And in the medical field, this is extremely important. That means going from what is real to what is virtual. And we do several studies, and we do quite routinely this approach in terms of knee biomechanics, where we can have the real experimental mechanics, but also we use computational analysis. We also do experimental tests, and also we replace the same machine to be able to really follow the real behavior in terms of force, in terms of displacement, in terms of moment, in terms of constraint, and so on. And we did, for instance, several studies analyzing the knee motion with and without prosthesis and so on. But I can tell you a lot of story. But and this especially to people that are not in the field, I can make nice animation, nice graph, and so on. But I'm not here to show how good we could be with Photoshop or animation and so on. We need to understand that when we do this kind of model, we are going to try to solve a problem with people that have issue. And the only things that we can do is to drive something that improves the trust. So when we talk about model, please, it's extremely important for us to have validation of the model, to really have that the number that we provide are realistic, are what we have. And this is an example of what we did. So we estimate the contact point. We have a robotic simulator where we apply and we put a real prosthesis. And we track the motion with this camera. We also have the kinematics, on the motion, different speed. And we calculate with a sensor the contact point, we calculate with the computer the contact point, and in the graph you see the blue and the red to really show that we were able to discriminate the same. And only if we have this, we can start to future, to trust what we have. And if we don't have this, we can have disaster. This is, for instance, an example of how in the past were calculated the contact point on top on a prosthesis on the insert, and this is what we obtain. So the contact is on the middle, on the lateral side. The different line represent the color, of the different line represent the flexion angle, and so on. We don't have any jump, we are more accurate, and we also strongly improve the evaluation of a patient. Pre-plugging, again, giving number. And what is really nice is giving information even if you don't have a monitor. And what we are going is really the use of augmented and virtual reality. This is a simple example of a tool, again, from Nico Verdonscott. This is the surgeon that is planning what are called an osteotomy. So you will see that is loading the information in terms of CT on the upper arm. We have the ulna and the radius, are the bone between the elbow and the wrist. And you will see that one, and he can play, he can move where he wants, and so on. You see that in front of him, he have a patient that have a huge deformity. You clearly see that these two bones that should be parallel, should be aligned, are far to be nicer. And so what we can do, we can realign because this situation produces a lot of problem. You see the blue is what is the target, automatically identify, and we can plan how to cut the bone to realign the structure. But it's even better because we can only plan what we want to do, but also the way that we as surgeons we can do to make that situation, before even starting, before even cutting the patient. I have already all the information of the patient before even opening. And we can plan and decide where to put the hole, the more stable situation, which plate that is the gray that we need to use, and after all the surgical treatment. So you will see now, it's really real time. So you can define the guide. So you have a patient that is healthy, you put this guide, are patient specific. So like a glove, they put in the right position, and in this right position you can put some screw, you can cut with the saw, you remove the piece, and with the plate you automatically realign in the position that you want. And in this way you will see that it's faster, safer, and also cheaper. So again, what we call today sustainable. Obviously, this was tested on the 15 patient. We saw a clearly improvement. What is also true, the box that you see this is what the patient received. So the patient doesn't need 20 boxes, it's only one box. You also have the bone before and after to see and play with the tool that you have. And that is an example of a patient that before was not able to externally rotate the wrist. One arm yes, the other no. Can you imagine all the problem, for instance, on driving? Still, take an object. I cannot put my wrist horizontally. And after we have a nice result, again, not only in terms, obviously it's important, of patient follow-up, but also what is really nice is the fact that the surgery is safer and is faster. Because consider that we need to cut, open, and see, and put a saw, and so on. However, I work also personally in augmented reality, but I work on the other side. Again, I want to increase trust. I work with some company like Verima and Witap, our Italian company. They work in general in the augmented reality, but we have another question. I mean, the surgeon uses augmented reality or virtual reality to see some object. But who tell you that these objects are really with the same distance of the real object that the patient has in his body? So we did several studies where we compared some of the example, again, sorry for the knee, and we were able to show and demonstrate that the value that we measure and also some length and axis have an accuracy of submillimetric. So most of them are even lower than a millimeter. That for us, it's fantastic. I know that, say, in some mechanical system, 1 millimeter of mistake, it's a lot. For us, it's very nice. And also great that we start to use the clinically. And that is another study, and we want to see how is good and what are the performance, and we really have a performance and improvement using augmented reality with respect of using our hand alone. And what we saw is that we really have a huge improvement as we analyze the two most common mistakes that you have in positioning, that is the positioning error in terms of angle. And we saw that, for instance, 97% of the 76 consecutive patients have a mistake less than 1 degree, and 88 on the other slope orientation. And also we saw that the error was independent by the level of deformity. We need to be honest that how we can pay this, because why not everybody using? Consider that every time that we add a new tool in a surgical theater, we need to consider that apart that we need to train, apart that we need to pay, is also that we have an increase of the time. The time of use of this that was in reality of 5 to 10 minutes, because in reality it was simple a glass that you need to use. And you have already the image of the patient. You can use to realign, so we have a sort of color code that start to become green with an accuracy of 1 degree, and this is why we have this great result, because it's so only when we see a good green. Pay attention that the cost of these are below 1,000. The other option, but I still put a question mark, is the use to robots, because the robots, it's more expensive. Usually a surgical robot in orthopedics is around 1 million. Robots. Robots exist in surgery. We also work, and most of the things that I will do, I can also send you a PDF of what we do. In medical field, it's more than 30, 40 years that surgeon use robot. I think everybody knows the Da Vinci system and so on. However, only recently was introduced in orthopedics. And so here we have some example of the robot used in orthopedics. And if I listen and read what the company that sell the robot put in their marketing the brochure, they say that I have an improvement of the surgery because I'm able to cut accurately and precise the bone. I'm able to re-put in the original position my leg to be able to move my joint physiologically. Okay. And what is true, they were very good in marketing. They were so good in marketing that, in fact, all the main companies today that sell prosthesis have a robot. Sometimes they develop their own robot, sometimes they bought a company that have a robot to integrate in the portfolio. And if you see how many, a study on robot multiplied by 3, by 4 in literature. So people also start to publish robot. And if this is a graph that I made last week when I was informed of this presentation, you see it's not even linear, as you can see on the light curve, but it's even exponentially. You say, why the last is below? Because it's April, and already we have almost this number of published papers on robotics in orthopedics. But we have a problem. We have a problem, and this is something very important in the field, because as I tell you at the beginning, we have different design, they have different features, so all the robots are different. And the surgeon usually chooses one. And you need to understand that that one is the one that you will use. So you need to know this, and sometimes this is not done. And there are a lot of features because all the robots that exist are different, even if they are aiming to the same stuff. What it means different? First of all, some of them are open, Some of them are closed. What it means, open and closed, is not that you can enter inside. It means that how many implants you can put with this robot. There are some of them that are open, that you can implant all the possible implants because they are owned by a company that don't sell prosthesis. But honestly, there are only two in the world. There are one Chinese, that is a T-solution, Think Surgical, and the Robin, that are my friends from Florence, but they don't give me money for that. And they just exit January with this Robin, with the idea, because their idea is to have the bird, but in reality to make the surgeon Batman. And that is a real story. And that they can do for any implant. But all of them, the real story, all the main companies in the world have their own robot. So I put the first that you see is the Rosa, and if you have the Rosa that is owned by Zimmer Biomet, you can only put the Persona sold by Zimmer Biomet. So if you have another prosthesis, you need to use your hand. You cannot use that robot. It's off-label, so it's not even legal. You are responsible, so. Image-based and image-less. What it means, how you can deal with the shape of the patient that you have. So sometimes the patient should be uploaded before, sometime after. And this is extremely important because you need to consider that the patient that needs a prosthesis, it's a patient that has a problem. So the shape of the bone is not great. You need to really identify, and we can have sometimes huge deviation from what is considered normal. So image-based, very easy. You can use imaging, CT and MRI. Some companies start also with a double X-ray, but the results are really bad. And if you have the image, you can also use this tool before doing surgery, like we did with the osteotomy on the arm. You have the geometry, you can see what is the implant, what is the size, how I should cut, and so on. And if I don't have it, if you don't have it, you need to measure intraoperatively. So the surgeon have a sort of pen. He starts to track the surface of the bone. The system record this tracking and make the shape. And he have a sort of morphing procedure to transform a sort of standard bone to the bone of the patient. Obviously, the first is better because you can have very good representation of the real geometry because you're using the real geometry. You can do all the planning, but it costs. It costs because, first of all, you need to do a CT and MRI that is not for free. Sometimes it's not even required. Not all the hospitals do this. It costs because you need to make the model, start to work on this. And I mean, surgeons usually work quite a lot. They want to work only during the intraoperatively, so they don't want in the week before or the night before to start to play with the plane. I open, cut, and do what I see. That is the advantage of not having image. Is less cost, less radiation. Yes, CT also provides radiation to the patient. However, you cannot do any pre-plan and consider that this morphing is an approximation, and sometimes you don't really have a good fit, and consider that also this landmark registration is in the hand of the robot that is very close that we cannot see. Surgical approach, what it means, how the surgeon uses the robot, because also this is different. Because the idea of the robot is the idea of the industrial robot, the robot do everything. And usually you do like this, maybe you see a light, if it's red you have a problem, otherwise everything is fine. That is not how it works. Usually we have 3 levels of interaction between the surgeon and the robot. Theoretically it can be active, in reality it's passive or semi-active. Active is the surgeon push a button and the robot operate. Forget it, doesn't work. Doesn't work, first of all, because the surgeon don't want to let another guy do the surgery. He wants to be, and also he's responsible. And he wants to always do what he thinks is correct. So the idea is that I will do everything. The robot suggests me where I need to put. So the idea is that the robot put my guide where I need to cut in what they think should be placed, and I will decide yes or no, and after I will start to cut with my hand. Or there are some other approach, like the semi-active, where in reality you have, as you can see, an instrumented saw. So you move the saw, and the robot decides to cut or not to cut, so you have the drill that go up and down or is lock to avoid if you think I'm cutting some region that you shouldn't touch. Question, how we can trust this? We did a lot of study on that. This is one of the examples that we did. The first thing is, let's see if they're really doing what they promise. Because one of the first things, as I show you, there is a lot of study behind robots. But pay attention. These studies are done in the lab. Okay, it's a good approach, but consider that we use the robot in a surgical theater with a patient, everything with the envelope of plastic for sterilization, with a surgeon that is using another engineer that developed the robot. So sometimes the field of application can be different. We did this study, and we find a very good result. And in reality, we are only one of the people that find good result. That means that a lot of people tell, it's true, we have a huge improvement in terms of position, and so on. But now we have a problem. Because, as I told you, we have a fantastic tool, but we need to see what happened to the patient. Because that is only the first step. And also, if we improve so much, because again, to be sustainable, we need also to limit the cost. We're paying 1 million to have this robot that is able to cut fantastically and very precise. But the patient feel a difference. Because up to yesterday, nobody used a robot. Today, yes. Why we need to switch to this if the patient doesn't feel? And now we start to see what the people find clinically. This is the first study. I put only systematic review, because obviously if I put some study from companies, they say that is fantastic. But these are systematic review, analyzing other study and so on. And they say that in reality, if I use my hand, it's better because I use less time to operate. And pay attention that less time have a huge advantage, mainly two. First, you have less time that the patient is open on the air to have bacterial adhesion. Second, it can maybe be operated more person in the same day. And every day I have one operation more, are also more money that come to the hospital. Even if they say that is true, I can feel that if I use a robot, as I have a better accuracy, patient complain less pain. Great, but if I start to use some statistics, unfortunately, this is not really statistically significant. Another one. He say, this study, that analyzing both total and uniconventional, shorter length of stay, and that is in reality quite important. The length of stay means how much time the patient stay in the hospital. And so if I'm able at the hospital to have a patient that remains less, I can have another patient entering in the hospital. Think that this can make really a breakthrough information according to also the social service that you provide. That is another one that he say, oh, we even put number, 14% of reduction long of stay. He also say, yes, it's true, if I use a robot, I stay more time. And it was, and then the last sentence was really strange in a certain way, no difference in total cost. We're using a robot of 1 million. I want to say two things. The first, that one of the authors is selling robot. Okay. But the second thing is American. So the cost of the procedure, it's already a little bit high. And so with this, you can have an easily comparison. Other last meta-analysis did create a lot of issue because it say no statistically or clinically significant difference between the two. So they see that the patient feel a little bit better, but it's because I spend more time. It's also considered that if I don't use a robot, I go faster. And as always, if you go faster, maybe that is also one of the reasons why you do it worse, that if you take your time to do the procedure. And so, last things. As an engineer, very fast, I consider that there is also a lot of improvement in materials. Today we can have smart material, because pay attention, we have bone, cartilage, and muscle, and we replace that with metal and plastic. Metal and plastic that, to give order of magnitude 1 or 2 times higher, so with a 0 after in terms of stiffness. Coefficient of friction 5 times more. So there is a lot of study also to try to make materials using additive manufacturing to have close to real properties, so we will reduce thickness. There are also companies that start to produce bone printed using animal bone. They're Franktomate. This is a Swiss company called EBI. And also another thing is to start to redesign completely the prosthesis. It's quite a nightmare from MDR, but that is another story. MDR is a new European certification for medical device, that you want to use what are called topology optimization, so to start to put metal where should be have and not have a full block of metal according to the force that we are playing, and so we can have very strange pattern, and that is something that it's not on the market, it's only on a research level. From our side, we are spending also more time to really understand if we can optimize and make a porous metal. We use 3D printing to check if we can tune the material in terms of stiffness and elasticity, and we were able to do it, so we can see that we can change the stiffness according to the shape that we are using. According to the distribution of the shape, we can have a sort of change in elasticity, and also we can tune it according to the patient that we have. Last but not least, very fast, because it's mainly ongoing today, is the evaluation of what these devices are inducing in the patient. So we have the possibility to use smartwatch wearables, something that we can give to the patient. They can track quite easily if I move or not, how I move or not. I can evaluate all of this. And I want to highlight a study that we do together with Professor Garone at ULB. This is something, it's a device, it's a brace that we, no. Okay. It's a goniometer. We want to measure the flexion of my patient. And this is a device that the idea is to give to surgeon very easily. And in front of him, having the patient walking, you can see really the 3D motion, 6 degrees of freedom of the patient. The surgeon needs only to push a button, and the machine do everything. You can record the data, you can make the history. Sorry for the sound, maybe it's too high. You can have all the curve, maybe too much, more or less. Obviously, most of the time that we spend to make this was to make for dummies, with the idea to say, first of all, the result doesn't depend on the position, because if I put another patient put, the nurse put, we have different result. No, it's automatically centered, and to make it as fast as possible. So what we need is only this to measure. You see, we are engineer, we use a caliper. We know that the surgeon will not use a caliper, but we need 2 measurements. We add in the software, and automatically you can have all the result. Companies start also to sell instrumented prostheses that are really expensive. They claim to use artificial intelligence, but after just 2 months, one paper exit telling we don't need it, because that implant will tell if the implant go okay. But you already put in the patient is using. If it doesn't work, you will see, because the patient is coming back. So there are still a lot of questions that say, what they provide, we can use a smartwatch to obtain. Why we need to insert a device with some batteries, with some electronics that also have problem with certification and so on. So it's not a good approach. Maybe I finish, maybe not, because in reality there is one very important thing that I forgot, is artificial intelligence. It's something that in reality span from the pre to post. It's something that enter quite a lot in the clinical field. And again, if you're interested, I can provide you some of the paper that I have. You know already everything. The idea you can process a lot of data. The idea is that I want to know what it works. The idea is that I want to manage medical and healthcare data to provide new way to disease. Great, very promising, a lot of potential. The numbers are booming. Everybody is talking of artificial intelligence in medicine and the new holy grail that tell you everything. Now we have a box, you touch the patient, you have this, and it's enough. It's true. It's true that everybody is talking, but it's also true that nobody's doing nothing. What I want to say that this is the number of AI submission in the FDA in US, and this is how people and which are the brand that are really using product with artificial intelligence. And this number there is 0, 1, 2. Who is using artificial intelligence? The real use of artificial intelligence in clinician is to compare image. Who is doing this? You see at the beginning, radiology. And that it's another story. And that it's a paper that takes it a few years ago, 5 years ago, with the head of the radiology group of Worldwide, that he make a special issue on artificial intelligence in radiology, and his editorial was, will artificial intelligence replace radiologists? And the answer was yes. In the sense that tomorrow the radiologist should work differently. Because artificial intelligence entering the field, we need to know how we can use it, what we can do, what we cannot do, and how to do this. But we really dramatically change how radiologists practice. And I don't have really an answer why it's not used in orthopedics. For sure, we know that there is a problem of verification and validation, that in orthopedics is quite difficult. It's really difficult because we need a large number of cases, and most of the time, hospitals don't even talk each other. And most of the time, the surgeon change idea from Monday to Friday, so it's difficult to have a close block. And as I told you, we need to know all the parameters, because only if we know the parameters, we can start to manage with data. And we need to know the target. And I tell you, there is no discussion. We don't know which target we want, because each patient is different, and so on. But last but not least, and this is something that I try to explain to the clinician, will you trust it? Because at the end, what the surgeon don't understand yet is the fact that the artificial intelligence, it's a black box that will tell you, do this. And I gave a very simple example. You have your GPS, and the GPS tell you, go right. And you think you need to go straight. You go straight or you go right. And the surgeon say, I go straight. So don't use it. Because artificial intelligence will tell you what to do. And if you don't follow because maybe you don't trust, it's a waste of time. And so I always say, will artificial intelligence replace orthopedic surgeon? No. Now it's finished? No. Because we need to understand two things. First of all, it's impossible to make everybody happy. I read one time a book that said that if you want to make everybody happy, you need to sell ice cream. And as we are surgeon or engineer or other things, we cannot make everybody happy. There is a lot of people that will never be happy. Last but not least, and that is a really problem, is a problem of conflict of interest. That what you find online, most of the time, have behind, and this is why I put my conflict of interest, we work with companies that sell, and they have a clear advantage to have some claim, and that is a nice study, they quantify that. So this is a study that they compare the result in terms of positive output or not, if you are royalties, if you have stock option, or you are a consultant or an employee. And you see that the first column is how often you say is good. The second column is how often you say is good, but you don't have this conflict of interest. And they report with a statistical difference that if you have royalty, stock option, or consultancy, your success rate, you are lucky maybe, it's statistically higher than if you don't have stock options. And with that, that if I put at the beginning, you can already exit the room, I want to give a very simple take-home message. First of all, that innovation is fundamental to everything, especially in orthopedics, so always it's important to be updated, but we can be updated and we can do everything and innovate only with trust and check the conflict of interest. Other things, to have trust, you need to know what you're doing, you need to have a good training, and consider that we became old, also the tools became old, we need to improve ourselves. Last but not least, even if everybody's looking for that, the Holy Grail doesn't exist. Everybody of us is different. We need to accommodate what we have to make everybody happy and not use the same things for everybody. And with this, I want to invite you to my conference in Brussels in September. I want to thank you, my group. Thank you a lot for your attention. Almost in time. I'm here for any question. You can always send me an email. And
Okay, thank you very much. It was really enlightening, and I worked a lot on the dental field,
okay.
Also the mental health field, but for the dental field, we reached the same conclusions for deception. So are there any questions in the audience? Okay. Yes.
We hear nowadays more and more of specifically designed prosthetics for the patient. So you design the prosthetic starting from the morphological I don't know how to say that.
Yeah, it's fine.
So what is your opinion on this?
Okay, custom-specific implant exists. For the hip, it's not really quite important because it's a sphere on a sphere. It's very important for traumatology because if you have a trauma, that means there is a car that hit you and you destroy all the bone. You want to rebuild everything close to the real. This is works. In Belgium, we have a different group that are working on this, different company. I don't want to make publicity. Eventually, later, I can tell you. But there are companies like the one that I interrupt that make really bone. And what is nice, they also do with 3D printing, with porous material, and so on. For the joint like the knee, there are two companies that sell custom-specific implant. There is one big issue. The first is that they're copying a joint that have a problem. Second, do you think that that is the best way to solve the problem? Second, the problem today, and that is a real answer that I have because there was a question that other people asked me, is that you recreate the anatomy in terms of geometry, but you don't recreate the anatomy in terms of material property, friction, and so on. Second, you need to trust a lot the way that you are putting your implant. Because think again the story of the circle. You can make the same circle, but you made a small mistake and you will have a different movement. So even if you're able to copy completely the anatomy, you need to be able to copy exactly the accuracy and the position, and that is not always true. After I became black belt on biomechanics, but consider that most of the issue that exists in the custom-specific joint is on the patellofemoral and not on the tibiofemoral. So you have a special hole in front of the femur where it's a sort of track. You need to consider that you have the railroad and the train. And the train needs to follow a proper railroad. Let's say it's not perfect with the custom-specific, also because when you have a problem, your bone is smart and it wants to evolve. That means we start to have what is called a deformity. And so you are correcting something that is already deformed. So not always a good idea.
Thank you. Another
you say
question?
I can always talk hours. So.
Yeah.
So first of all, full disclaimer, I don't have a white belt in biomechanics. Yeah. Anyway, you talked about having patients less time in hospitals so that you can send them away. I'm thinking about having doctors unavailability, so you don't have many doctors who can perform operations sometimes. Have you also thought about teleoperations, so where you can teleoperate, from remote locations?
Yes, that was something that was quite booming, not in orthopedics, when the first robot exit in the clinical practice. Consider the master-slave robot, the story that the surgeon can be in New York and the patient can be in Memphis. It's true, they exist, but it's not really popular, because the main issue is that the surgeon cannot be in front of the patient. The surgeon, sorry, cannot be in front of the patient, but should be close to the patient if something goes wrong. So in reality, what it exists, and this is really true, and we are also working on that, on the possibility to visit or check the patient at home or in other location, not to let the patient go to have in front of the surgeon. So using also, for instance, watching like this, you can ask the patient, that was also working in some field during COVID, that we will not ask to the patient to go to the hospital for the visit, to have a preliminary check they can do at home. That is really a good benefit to improve these things. In terms of having the patient in the hospital, a lot of studies have highlighted that the best place that you should be after operation is at home. So you don't really need to be at hospital. Usually people, for instance in US, but also in Europe, we start to have the fast track. That means to stay in the hospital one day. That you can understand is one working day, is less than 24 hours. This depends on the state. But that is also what everybody is working. And they have also, unless you really need to be in the hospital for several reasons, but consider that also the anesthesia for this kind of treatment is local anesthesia. It's not that you have a full anesthesia. And so unless you have problem of heart or other things, you can be at home. That is, yes.
Thank you.
Please.
You say that in the operation time was longer when you use the robot. Is that because of robot preparation time?
Yes. That is a good point. The story is that depends also who's writing the paper, because you can say that time of surgery can start when the surgeon starts to cut, or surgeon operation time start when the patient enters the room. So we can discuss. So for sure, when you use a robot, you have the time of preparation of the robot, the calibration of the robot, and most of the calibration of the robot need to be done in front of the patient, because you need to explain to the robot where is the patient. And this is something that you need always to add. Most of the company, because this started sort of an evolution of what in the past was called navigation. And some surgeons claim that if you go quite fast, you can go closer to the manual, but at least you can have 5 minutes, 10 minutes more with, honestly, an operation that can last 1 hour. So it's not 10 minutes on 20 minutes, but you still have from 10 to 20% more time. Obviously, if you want to talk bad about robot, you can say, yeah, I need also the preparation of the robot, I need to clean the robot, I need to clean the room, but usually we consider incisions from the first incision to the last closure.
All right, thank you. Okay, maybe to finish, one last question on my side, because for some of us at the European Robotics Forum, we saw one presentation of robotics in healthcare, and he was addressing that already without even speaking of robots, healthcare can be quite polluting, and one image was also how much products are used for just one single operation, and it can feel a space a bit larger than here, or it was maybe at one of the BrIAS events, I don't remember.
Yes.
You have a lot of insightful comments about various aspects of sustainability. On the environmental one, what are your thoughts on the current state of orthopedic robotics?
I will tell you, orthopedics is the worst in terms of pollution. I just read an article today, but I didn't put that they waste 60% more than the other operation. Because consider that to do a surgery, we need to have boxes like that you need to put in the place, close, and after go to sterilized. And sometimes this box you use only one tool. For instance, you have one box for the femur, one box for the tibia, one box for the implant, one box for the trial. Because you need to cut one box, you need to see if it's okay, so you have what is called a trial. And if it's not, you need to go again and recut. And when it's okay, you put the real prosthesis. And after you closed. This is what I saw, maybe it was too fast. The idea really of using this innovation is really to reduce the space of material that you can use because you have only one guide. you already know the device that you can use. One thing that maybe you don't realize is the fact the dimension of the implant, because my knee is not equal to you, we decide when we open. We open and we take measurement. So before, we don't know, and we come with the box with all the implant size, from the extra small to the extra large, and we use only one. And another thing is that we have two bones that touch each other, and sometimes touch like this, sometimes touch like that. So you have even different thickness. So the idea to anticipate dimension and size is really promising. And one of the things that we want to do is this. There is one issue on that. The big benefit of this story, the big benefit of having that is mainly for the company. Because the surgeon don't pay these kind of things, the patient don't realize that. So there is some improvement, but it's not really worldwide important because we don't feel it. But it's true that we have a lot of box, a lot of plastic, a lot of sterilization. We are working on make some reusable or make some part that we can do, but it's true that, when I say sustainability, it's mainly to reduce cost for the society, make something better, let the people go to work before and so on. In terms of wasting material, we are going on the personalized medicine that is not custom-specific prosthesis. That can allow a reduction, because if we know what we want, we can do faster and better. But there will be a reduction. We cannot avoid all these things. And it's really an issue.
Thank you so much for being also so open and honest about your field. So thank you very much. A round of applause.
Thank you.
Three important messages before the coffee. So there is coffee,
Bravo.
there is cake. So all the good things are here. We have also two events coming up very soon on the 26th. And for War and Peace, it's the 2nd and 3rd of May. So please go on brias.be, register, and it's important. And please share the good news. For those of you who are interested, at the 4th floor of the building here, we're building AR/VR cave, other name given for a virtual reality room, where we will have a lot of digital twinning, for instance. So if some of you are interested, I'm taking a small group or large group right now during the break to see a little bit what's also in the building. Thank you.
Okay, so good afternoon and welcome back to everybody, both in presence and remotely. And it is really my pleasure to introduce our next speaker, that is Dr. Cotorruelo. So Dr. Cotorruelo is one of our junior fellows of the Brussels Institute for Advanced Studies. And I could name his presentation of today something like, are you ready for some good math? In the sense that what Andres did during his PhD and then afterward was to work on mathematical solutions to find sets that are important for the construction of control of system subjects to constraints. This sometimes might seem kind of abstract, but at the very real time has very practical applications. And so it is really my pleasure to present him also because he had his PhD in our department, and this was something we did together, so I'm particularly proud of some of the results that are in there. So I leave the stage to Andres, who will delight us with some interesting math.
Okay, good afternoon, everybody. First of all, sorry to disappoint, there will be almost no math in the presentation. Yeah, when I had to put together the presentation, I thought, well, either I make it for Emanuele, Fabrizio, and Eduardo, or I make it for the whole room. So I sorry, but like majority won in this one. So instead of going knee-deep into crazy math, which honestly I find kind of beautiful, I'll just give you a taste for what is my research field, what is the field of set-theoretic control. And I will mention my contributions very briefly. So, sets. When I was learning English in school, set was actually the word with the most meanings in the dictionary. But yesterday I looked, and apparently now run is the word with the most meanings. And I can't go forward. That's okay. There we go. The meaning we will use today is a collection of elements, and especially mathematical ones, such as number of points. For example, instead of saying 1, 2, 3, 4, 5, 6, I could say the set of numbers between 1 and 6. Or instead of saying a circle, I can say, well, it's the set of points that are at a distance of maximum 1 meter from the center. And why would I do this instead of just listing the elements? Well, working with sets is inherently powerful, because I can make statements about the whole set instead of making statements about the elements. In this case, where I'm listing the numbers from 1 to 6, well, it might not look so interesting, it's only 6 elements. But if I want to prove if a circle of radius 1 can be contained in a square of side 2, if I do it point by point, it's going to take forever. There are infinitely many points. But if I can prove a thing about the whole set, I have it in just one stroke. Okay, this is nice and all, beautiful, but it's very mathy, right? And I'm an engineer, even though when I was doing my PhD, I was like the mathematician of the lab. So we have to keep it applied. And I did my PhD in a systems and control group. So it was applied to systems. And I hope I don't surprise most of you when I say that in systems, we want to describe how a system behaves. And for that, we use the concept of state. State is the number, the minimum number of variables that is required to describe a given system, or the evolution of a system, rather. It's all very nice and abstract, just how we like it. But just for you, I'll make a couple examples. If our system is looks like this, a couple tanks, one that pours water onto the other, if we describe this mathematically, the minimum number of variables that we need to describe the behavior of this system is 2. The level of the first tank and the level of the second tank. If, however, we have a pendulum, what's the minimum number of variables that you need to describe this? You could think, well, just one, right? The angle that it has with the vertical, that's it. But if I show you a picture of like that pendulum over there, you don't know if it's swinging left or right. So we actually need 2 variables again, the position and the velocity. With the concept of state already introduced, I would like to introduce you as well to an old friend of every control engineer, the mass spring damper system. It's a very simple system that, despite its simplicity, it's been widely used to model, for example, valves. And don't mind this minimalistic representation. It's, in reality, it looks like a mass, a block of, let's say, metal, connected to a fixed point via a spring and a damper, surprisingly. So, on the right side of the right-hand side of the screen, I'll show you a graph where we can see the position and velocity of this system when we tug a bit on the mass and release. Ready? Ready? There you go. As you might expect, the mass oscillates back and forth between the resting point until it converges to this point. And to be fair, if we look at the graph on the right, it's not very informationally dense. We can see that it oscillates, but maybe having the dimension of time there kind of muddies things up a bit. So as we said, this has 2 states, the position and the velocity. So what happens if I say, okay, let's get rid of time altogether and let's plot velocity versus position. So I'm gonna run the simulation again. This time on the right-hand side, I'm gonna plot velocity versus position. Let's see how it looks like. Okay, we can see it makes a nice spiral. Maybe it was me that I was a bit smart and I chose the point that makes this pretty figure. So let's just use another initial point and simulate. Let's see what happens. Turns out, same spiral. And if we analyze the system and its model, we can compute a little arrow, what we call a vector, in every point of space that will tell me where this trajectory will go, depending on where it is. And just because I like animations, here's another one of the trajectory on top of this vector field. And as you can see, the trajectory follows what the arrows mark. Okay, you can say, right, nice animations, blah, 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 but you mentioned sets. Where are the sets here? Okay, hold your horses. I needed to introduce all of this to be able to present the main character of this of today's presentation, which is the invariant set. In math, when we say invariant, it just means it's an object with a property that doesn't change. In this case, the property is the fact that the state, once it enters the set, it will stay inside the set forever. Why should we care about this? Well, this, if you think about it, it's actually very powerful, because if I can prove that the state is inside the set at some point in time, the state will remain in this set forever. Meaning that I can say things about the system by just analyzing the set itself. So, again, one more animation. where I plot the invariant set for this system. And as we can see, once the trajectory enters the set, it will never leave it. So, pretty cool. It's really nice material for animations, but you might be interested in how do we compute these? Well, luckily for us, towards the end of the 19th century, if my memory serves me right, a man called Alexander Lyapunov came out with his PhD thesis in which he presented what we now call Lyapunov functions. And I will not go into detail about this. It's really a fascinating topic, and after the talk, if you're really interested, you can hear me nerd about it for a few minutes. What I just want you to know today is that this is the general form that a Lyapunov function takes, and that everything at the left-hand side is the shape of the invariant set, and everything to the right-hand side is the size of the invariant set. One more thing, when the right-hand side, so the gamma there, is 0, the Lyapunov function indicates the point to which we converge. More animations, just because. There we would have a sample Lyapunov function where we change the right-hand side, and as you can see, we converge to 0. And if we change the left-hand side to something a bit more interesting, we would have, for instance, this thing. Okay, so now let's rewind a bit. I've talked about sets, and I've talked about control, but there's an elephant in the room. It's the word constraint. Right? So what do we mean by constraints? Here, by constraint, I just mean the limitation or a restriction of a system. And to put this into more concrete terms, if we have a robotic arm, we can limit the speed of its joints for safety, if it's operating around humans, for example. If we have a combustion engine, we want to keep the air-fuel ratio to a number for performance. Or these constraints can come from actual physical limitations. For instance, in a chemical reactor, the maximum pressure that it can stand. Okay, so remember how I told you that the mass spring damper system is a great model for a valve? Let's try and draw that. I hope I made it sufficiently clear. So how would constraints look in this case? Well, for instance, I can't push the piston more than 0.5 to the left because I would actually break the damper. And I can't push it more than 1 centimeter to the right because that hits the other side of the pipe. Okay, sufficiently clear? Now, how do these constraints look in the state space that we plotted before, so velocity versus position? Well, as we said, anything to the left of minus 0.1 cancelled, and anything to the right of 1 is also a no-go zone. There you go. Now, so far so good. We are putting together the pieces of the puzzle. And how would an invariant set look like if we wanted to draw it here? And bear in mind that we want this invariant set to be strictly inside the constraints. Well, if I want the largest one, it would look something like this. I hope it's clear, but for those who can't spot it, it's orange dashed ellipsoid. Okay, So intuitively, to compute the largest invariant set in this situation, I would have it to be tangent to one of the constraints. Because otherwise, I could just make it bigger until it touches one constraint. Okay, that's nice, but unfortunately, that's somewhat easy to do. So let's ramp up the difficulty a bit. If you think about it, so far I have only shown invariant sets or systems that go to 0. But if we think again of the valve, that might not be the smartest idea. Why? Because if I have a valve, it's to use it, and I might want it to open and close at will. So I need to arrive to different points of opening of the valve, not just one particular one at 0. So if I want to arrive to a different point, how do these sets have to change? And more specifically, how do the Lyapunov function has to change? So first of all, I would need to move the center of the Lyapunov function. And as you, I don't know if you can see it from there. I see people struggling a bit. Okay, so if we move the center, how does it look in the Lyapunov function? Well, I just need to introduce a new variable, r, which is the reference, so the point I want to arrive to, in the function. And this is quite easy. This can be done in seconds. Now, I think that you see a problem with this animation, right? Because the size is static, it intersects the constraints at times, meaning that the size of this set has to change. And if we change it to something like this, we can see that when we get close to the constraints, the set becomes smaller, and we're far away, the set becomes larger, as we expected. So what needs to change down there in the Lyapunov function? Well, the right-hand side, the side that controls the size. And, well, this is not so easy, but it can still be done. When can it be done? Well, when the shape is an ellipsoid, like there, and when constraints are linear, like there, meaning straight lines. This is quite easy. This can be done in closed form. Emmanuel's looking at me weird, but because I say it's easy, but it's one of his previous results. It's easy but beautiful. But now, what happens if I want to switch it up a bit? If I want to use different shapes of Lyapunov functions and different shapes of constraints? For example, let's say that the constraints and Lyapunov functions are polynomial. Well, apparently that's not so easy, and it's hard enough to grant a PhD, specifically to me. Here you can see an example of a very circusy result, as Emmanuel likes to say, that I had for the thesis, where as you can see we have a square with rounded corners that can fit snugly inside a circle, no matter where it is. We have some other results for the previous case where we have an ellipsoid, but constraints are no longer linear, so we allow this ellipsoid to rotate and change shape. And actually, this result is for a mass spring damper system that is actuated with an electromagnet. So it's a real example. And I can see it in all of your faces, this question. Cool, but why would you waste time on this? Well, turns out it's quite interesting. We can use these kind of sets to be the end of a prediction. If I am predicting where I'll be in the future, ideally I would predict until t equals infinity until time ends. But of course, that's not realistic. I have to have a finite prediction horizon. And a good way to end your prediction is in a safe invariant set, an invariant set that does not intersect any constraints. Because when you arrive there, you know you can just let go of the steering wheel, because whatever happens, no constraints will be violated. Interestingly enough, these sets can also be used as a measure of safety. The size of these sets are an indicator of how far I am from the constraint. If I'm very close, the invariant set will be very small, whereas if I'm quite far, the invariant set would be quite large. So it gives a feeling of how much margin of maneuverability I have, more or less. Okay, so I hope I convinced you that with Lyapunov theory, we have a sort of systematic approach to computing these sets. But in life, whenever you gain something, you lose it from a different place. So what we lose here is that generally we don't get the largest sets here. But in my field, and in many other places, bigger is better. So, what if I wanted the largest invariant set? Well, turns out they exist, and they have a special name. They are called the maximal output admissible sets. O infinity for short, quite a cool name. Anything that has infinity in it is quite cool. As I said, they are the largest invariant sets, and now I have to say to all control engineers in the room, please forgive me for what I'm about to show on screen. Let's take a system with input R and output X. So yeah, pre-stabilized, and I assume full knowledge of the state, so that's clear, all good. So how could I compute this, this maximal output invariant set? Well, an easy way would be, okay, I'm going to test one reference, one value of R, and I'm going to wait and see if my X violates the constraints. And I could plot, I could plot it and imagine that for that specific value, everything's okay. I color it green. Imagine that for that specific value of initial state and reference, everything goes well, color it green, green, red, red, red. And I could go on like this forever until I find a sort of a good approximation of this set. I hope you agree with me that this is not a good way about it, and we have to find a more technical approach to this. Luckily, there is one. A good way to do this is to what we call project constraints into the future. So basically, I'm standing here at time 0, and I say, okay, at time 1, I don't want any constraints violated. And additionally, I want that at time 2, there are no constraints violated. Time 3, time 4, time 5, etc., up to time equals infinity, which actually that's where the infinity comes from in the O infinity. Right, so if you are following, this is more or less like constructing this set by cutting. We start with an initial set, and we start removing things that will violate constraints in the future. But the key aspect here, and it's a problem common to a lot of areas in life, the hard thing is knowing when to stop. And if we have linear constraints and a linear system, it's quite easy. We know exactly when to stop. We stop when we can't remove anything else from the set, when adding more constraints doesn't add any information. Polynomials, that is not the case. It's hard to know when adding another polynomial will not add any more information. Well, that's another of my contributions. And in the screen you can see a video for this same system as before, the mass spring damper system that is actuated with an electromagnet. And as you can see in the video, I couldn't make Mathematica do a nice rotation of the figure. So that's me doing it by hand. And I can see the same faces as before. Cool, but why? Well, turns out that in many cases, predicting safety by instead of making the explicit prediction, just by checking whether you are in this set or not, is much more computationally efficient. So we arrived to the end of my talk, and I would like you to leave with a couple take-home messages. And that is that constraint control, as Eduardo will surely know, can be computationally very heavy. But if we're a bit smart about the ways that we do things, and we pre-compute as much, and we encapsulate it into set-based arguments, we can potentially reduce drastically the demands of advanced control algorithms. Thank you very much for your attention, and I'll be very glad to take any questions you might have now.
Okay, very nice talk. You always have been working with autonomous systems. Have you considered also controlling variant sets for your this?
We have worked mostly with systems that are pre-compensated, and they have a reference-like signal.
Any other questions?
So, first of all, very, very nice talk. I very enjoyed it. I think I will tell my son I want to convince him to do these kind of things, and maybe this is a good way to do that. So, you use polynomial tools, right? Like SOS and...
Yes.
I try to use those kind of tools. They are wonderful. They scale very badly. So what was your experience in that?
Exactly that. For toy examples, it works great, and you can do crazy things with the TV screen shape and a circle. We found out that when you base your optimization problem in Stengel's positive Stellensatz, sorry, Germans for the butchering of the pronunciation, things tend to not scale well. However, if you use Putinar, we arrived at very, very good dimensions, or like number of dimensions. We arrived at dimension around 10 with good levels of precision.
And as you said, you can pre-compute these, so I mean, you can take your time. But,
exactly.
But sometimes it's not enough.
Yeah, sometimes, well, it was like a couple weeks of calculation and then error.
Did you play also with using other polynomial bases like Chebyshev? Everybody says it's, but it's hard.
Yes. So if you go in the literature, everything by Parrillo and Johan Löfberg, Chebyshev bases are the best, and they are gonna solve your life, cure all your back pain and everything. But that's I found out that it's for me it didn't work.
Okay.
I don't know if well. Turns out the software I was using didn't have native support for these other bases.
Okay.
I implemented it myself, and I couldn't find any improvement. So I am willing to take the blame for that.
Yeah, no. Also, I never tried, but that's the usual answer. But since you
they say that they are more stable, but my experience says otherwise.
They are, of course, because there's nothing less stable than the classical polynomial basis. You can easily, but
epsilon more stable, maybe.
Thank you very much.
Thank you for your question.
So my question would be very cool, but why? What application was the valve for, and could you, by applying your method, improve in some level or like reach your goal, whatever it was?
So yeah, the example that I used in the presentation over and over again, the electromagnetically actuated mass spring damper system, it's a model that is used for valves in, for example, the intake of a car. So if you think that to have your ECU on the car instead of needing an Intel whatever goes in a car, I don't have a clue, you could instead have an FPGA or a low footprint type of processor, because you pre-computed all of it and you just need a bit of memory to feed it and not a lot of computational power. Well, that's already an increase in sustainability on the economical side and on the energy side.
So the goal was to decrease the computational load?
Yes, yes.
Not like the performance of the valve or anything?
And it's usually a bit of a give and take. If you increase in computational efficiency, you probably lose a bit on performance. But in our lab, we are quite minimalistic, and we like to do things with as least resources as possible.
Thanks for an amazing presentation to present this difficult topic in such a nice, simple way, as usual, Andres. I was wondering, maybe it's a silly question related to the last picture that you showed to us. What about if you don't know the parameters of the model? Imagine that you have the two interconnected tanks and the density is changing, or the mass damper system, and you lose properties over time, or a bit of the mass. How would you expect that constraint system, constraint set will change?
Luckily, set-based control is super powerful. So we can use set-based arguments to answer that question. Usually you can translate these sorts of uncertainties into a set-based uncertainty. There, in all that I showed, I assumed that I knew perfectly the state. But instead you can say, look, my sensors are not so great, or I don't really know the parameters of my system. So I know I'm in the vicinity of this point, more or less, with a radius of more or less this. And then what you can do is perform an operation that's called the Pontryagin difference, that I actually also put in my thesis. We have some results on that, pretty cool, pretty visual. Actually, I kind of regret not showing it. But yeah, it can be tackled within the same framework.
So is there any other questions?
Oh, thank you. So, in model predictive control, you use invariant sets as a way of guaranteeing sort of designing sort of guarantee stability. You don't use it in this sense here, or you're using just to check if your let's say your system, your control, your autonomous system is stable or where is stable? Is that so? Or?
We did apply it as the terminal set for MPC for tracking.
Okay. That's
it's a direct application of the thing. So I find it quite beautiful that it can be applied in the big beast of constraint control, MPC, with all its optimization and computational load, and also in the low computational cousin of constraint control.
All right, we have a question from a person online. She says, could you please say, it's a question from a designer, not a mathematician, okay? Could control be a separate variable in some perspective for robots with explicit quantity?
I apologize. I am afraid I didn't understand the question.
I think they say that could control be a separate variable in some perspective for robotics, in terms of robotics, with explicit quantity.
So I'm asking the person that asked the question to elaborate a bit. Maybe they can connect their microphone. Is that a possibility?
No.
Like how much is control? Sorry if it's a strange question.
How much is control? Yeah.
So I still don't understand. I think that if you connect your mic, we can maybe precise a bit more and I can provide you with an answer.
Yes, we can.
So is your question, wait, I think I can do this, right? No, it's so maybe we can communicate like this, like, sorry, the system wasn't ready for for people talking into their mics. So you were asking the question that if it's possible to add a variable in the model to account for other people's control, is that it?
Or, for example, to account if it's a machine guiding what is happening or people.
So the way that I see it is that would be two different modes of operation. Either you have it operated automatically by the machine, or it's operated manually. This sort of research could have some application if it was operated manually, in the sense that it could provide you with an estimation of, is what you're currently doing safe? Or are you going to have problems in the future if you go on with this way of using the machine? That's actually an interesting application. But I must say it was mainly conceived for more automatic type of controls. I don't know if I answered your question. If not, feel free to elaborate. All right.
All right, welcome back, everybody. It has been the noisiest day possibly, so thank you for being all here and hanging in there. It's our pleasure now to have Dr. Alex Partridge from the National Robotarium in the UK to present the work on Grow Your Own Robot. So Alex, I think it's also one of your last days, if I'm not... Yeah. So with sadness, please do your presentation. Thank you.
All right. Hey, everyone. I am unorganized, so I've only just realized that I'm giving this presentation. Great to be here. Luckily, I gave the presentation to some supervisors earlier on, so you're getting take 2 of that. Okay, so I'm from National Robotarium in Edinburgh. Most of you have already seen this already. Lovely. Come visit us. Great. I am from the UK. I did a PhD in reflex response robotics. Done some papers. Good job, Alex. But the main thing that I was interested in over recent years was recycling strategies for soft robots. So how we take the materials that we use for the devices that we make and make them more sustainable. You're already aware of this probably because I gave a talk previously, so we'll skip through that as well. The fish is dead. Poor fish. Oh no, everything's going weird. Okay, so for those online, you maybe haven't seen me before, so I work in soft robotics, which is squidgy stuff. So here we have a nice squidgy gripper. This is used in the Amazon facilities to pick and place. It works like this. It's just a fancy balloon. You inflate it, you deflate it. It will have a state change. And you get really nice compliance once it's actually grasping. So it's just on or off. There's no need for control over position. You can then use that fancy balloon to make nice weird things happen, like your teddy bears walk around. There's other devices you can create, like this one, which is a tube of plastic bags that can wind around like a vine, which is absolutely phenomenal. We can use things for subsea. We can make little exploding robots like this little octopus. We've got the self-healing fancy balloons that we've created here in Brussels that I finally played with for the first time yesterday, which was quite fun. And we can even make little robots made out of tadpoles. You're welcome, world. All right. So, I'm sorry for repeating myself, guys. It's going to be so boring. All right, soft robotics. We're valued for 5 billion by 2025. We're valued for 6 billion by 2026, and then we dip down to 3 billion for 2027. It's a real shame. But we're growing, which is nice. But with growth comes waste, and so, we're producing a lot of waste as a world. We need to start addressing the things that we're going to be putting into landfill before it gets there. So that's where I came in and thought about soft robotics is growing. How do we actually mitigate the things that we're putting into the earth? So the first things you can do is simulate rather than create. So rather than actually creating all the devices that we want to start playing around with, especially in the developmental phase, simulate it. So let's figure out actually what is it that we actually are aiming for. Can we create a close enough simulation before we actually put our hands into the materials that we're going to then throw away? We can start using more recyclable materials in that development stage as well. So once we actually got that simulation, we can think about things like clay and things which are endlessly usable, like you were as a kid. You would just grab it, you'd play with it, you'd make something. Okay, cool. The form is right, ergonomically it fits. Perfect. We can now move on to actually creating the device itself. Same with paper and other materials. Reuse, repurpose. So one of the main materials that we use in soft robotics is silicon, which is an elastomer. To create devices, you have to mix up 2 parts of elastomer, then pour it into a mold. Quite often, you then have too much material. So if we've then got waste, we can then throw it into another mold that you can then use for something around the house. For example, this little scrubby that you would use for doing dishes, or a heat pad for when you've taken your pot off the stove and you want to put it down, rather than going out to the shops and buying something. Use that waste material that was otherwise going to go into the bin. And you can make the molds really simply in CAD, or just download them online from Thingiverse, that kind of thing. Final thing I looked into was recycling. So you can actually take silicon parts, you can granulate them down into a fine, not quite powder, but small granules. And you can then flood that with elastomer, pristine elastomer. So you then have a part new, part recycled device, which is still functional. And I made it so that the way that we do that is incredibly accessible to everybody and very, very cheap. So there is a £15 coffee grinder from Amazon. You just cut your pieces up a little bit smaller, throw them into the coffee grinder, add some icing sugar to reduce the surface friction of the particles, whiz it up for a bit, and then you can start sifting down so you get a particle size that you want depending on your device. So for example, you have a mold where you've got quite fine elements, then you're going to want to like grind that right down to like sub 1 millimeter. If you're not really that worried and you've got a bigger part, you can go for 1 to 3 millimeters, it's all good. But then just wash off the icing sugar, throw it in the oven, and you've got your bits. Cool. And it works. Grows and grows and grows. Can pick up ducts. Nice. Research. Cool. All right, the reason I'm here. So I came in to play with some mycelium, which is the root structure of mushrooms, and we're using this as the base material to then make some soft robots from, rather than using silicons and things which are, okay, they're now recyclable, but it's still not great, because at some point it is going to be a dead material that goes into the ground. How about instead look at biomaterials which already have characteristics that we want to explore? So the mycelium that's been developed in VUB, it's been developed for like a leather-like material, which is really beautiful. This is a nice tortilla version where it is just mycelium, there's no backing. But we also have this, which has been treated. So this is actually a sandwich of mycelium, then linen and a bioadhesive, and then another layer of mycelium. So you get the mycelium on both sides, and it has like a really beautiful leather-like feel. And I was tasked with coming in and trying to make some cool devices out of this. So I started around playing with cable-driven. This is just to test material properties, like does it actually allow us to pull with a little bit of force, then bend up? Does it have an elastic return? This version is actually quite an old piece of material, so it did have elastic return, but it was a bit crunchy. I've since had better results with other materials. I wanted to test if we could use silicon on it as well, so we can actually interface this biomaterial with some of the other soft robotic elements that exist already. And it does adhere, but because of the mycelium layer being very thin and biological, it does tear off very easily. So potentially you could interface, but it would have to be with very low force applications. I then looked into gripping systems, so starting to play around with the material and how we can actually go from a 2D to a 3D state change that can actually be a functional device. So this is my first foray into gripping. It's a nice little fortune cookie that cracks and isn't great, but for day one, wasn't too bad. And yeah, you can see the cracks here. So this is an old piece of material again, so this is where we got to last time. On to the new stuff. Great, a few minutes. So, developments. So since then I got the new material. It's much fresher, it's less prone to cracking. So I first looked into kirigami. So if we think about ways to make things go from a 2D to a 3D, we can think of origami and kirigami. These are traditional methods that we've used in the past. So here is a kirigami gripper. It's straight out of the literature from soft robotics, but I've just applied it to mycelium. It's really beautiful. So you just apply a linear force in both directions, and then you get this really nice cupping motion, and it's able to grasp quite effectively. So I was very happy with that. You can see there's quite high stress on those hinge points, but actually there wasn't any cracking, and I've done this quite a few times to show it off around the lab because I'm quite proud of it. But yeah, it still lives, it's still doing quite well. I also went for a needle nose version. So this is more like a tweezer. And again, it's very functional. So the tweezing element here isn't conforming to anything because there's nothing to pick up, but if you were to place a ball, like a marble or something in the middle, it's actually able to then conform to the shape quite nicely. Really beautiful design. Not mine. Very much stolen. But the mycelium is all me. Also looked into manipulator design. So this is, again, cable-driven. This is just a planar mushroom that I've cut into pieces and then made a very, very simple cable-driven actuator. It was all right. Again, this is old material, so it didn't quite work out. I then wanted to take it to a spatial case. So this is where it can work in 3 dimensions. So I made a cross that then went down the middle, so like a backbone that was a cross-section. And again, we can manipulate it. And it moves around. So it was actually much different than I expected it to be. So I did actually spend some time twisting it and trying to break that spine to then allow it to move around a bit more, and it did, which is quite good. But this is all from one sheet of material. I actually think if we were to play around with the stiffness of the material, which you can do with the mycelium, you can kind of play with that backing, the fabric backing that you're using. You can use something a bit more elastic. If you have a bit more of an elastic spine and then you do the same thing, I think it'd be quite effective. And the last thing I looked into was pneumatic actuation. So I've shown you some fancy balloons. Can I make some fancy balloon mushrooms? Hell yeah. So actually, surprisingly, it can take a pneumatic pressure. So I just sealed it with some super glue, really simple, on a desktop, and it blows up like a balloon, which was quite surprising, but I was very happy about it. So from this, I wanted to then try and make it more fancy, like the ones we've seen previously. So I started with laser cutting. So this is just pure mycelium. There's no backing in here. This is just mushroom. Apart from these like smaller pieces, they actually have a bit of a fabric backing because I wanted something a bit stiffer in the middle. So I cut all of these, and then I started to make individual balloons, which I will then stack together. So you take this, you add that. So then if you've got a pneumatic input coming through that little hole, once we fold this over, you've then got the ability for that air to then come up into the pocket. I'll try and show you. So I seal up the edge, and then this is your pocket. So you fold it over. There's an air inlet going through the bottom, but also it allows air into. Nice, cool. Okay, so I take all these pockets, I then sandwich them together, so stack, 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 and I end up with this little like ribbed guy. I was really impatient again. I use super glue, and it's not great for sticking mycelium together, who knew? So it is very leaky, but it only leaks out of the sides where I've actually made that seal. It doesn't come through the body of the mycelium, which is promising. So then I start to play with the fancy self-healing materials that they have in the lab. This is actually made from castor oil, so it's still a biomaterial. So again, we're still playing in that biodegradable landscape. Use that as a glue to then stick it together, and it did work. I didn't have time to get any video for that, so here finally is just a super glued one, which is, yeah, it's all right. But you can see the principle, right? So you've got it inflating, they push apart, and that's actually going to cause a curve, which is going to be able to make a gripping finger. So I'm really proud of this. I think it looks quite nice as well. So next stage is publicating, and we actually have some really nice inherent properties from the material as well. So it's something that was tested by Toyota, because the guy at VUB that made the material wanted to throw it out there and see if any companies would actually want to use it. And one thing they came back with is they set it on fire and it put itself out. And they did that repeatedly, and they're like, yeah, no, it doesn't want to be on fire, which is pretty cool. So I can actually make grippers which are biodegradable and also fire resistant, and that's quite something. So like, that's not something you'd expect either, which is quite cool. Like a biological material burns, it loves burning, but this stuff, it's all good. So that's kind of like the angle we're going to take, is, you know, trying to use these inherent properties, and also like the fact that it feels really nice as well. So if you're thinking like artistic robots, like this is actually quite a nice space to be working in. That's me. That is everything I have to say. Thanks.
All right. It was really complimentary to a few of the presentation on the OM and the BrIAS side as well, so thank you very much. Are there any questions? Yes.
Thank you. I think in 1 month we have seen your starting, as well as after 1 month we are seeing some progress of what you are doing with the things. But what is the next thing you are going to do? Because now you see that it's kind of behaving like a soft robots. Mm-hmm. How you are going to test the biodegradability test and this kind of, how you are going to make it more application oriented of this kind of robots?
So this month's day was all about trying to find that function, right, and find application space. Now that we have some applications, it's just about testing everything that's been created within its scope. So for example, the pneumatic actuators, just inflate it till it bursts, and then we know exactly like how much inflation you want to be putting into it. It's a kind of modular system, that pneumatic one, because you just kind of keep stacking until you've got a length that you like. So we can start playing with that as well. We can start like looking at modeling length versus curvature versus carry, capacity, that kind of thing. Going to do some burn tests, because why not? I want to set something on fire and pick it up. I think that would be a perfect conference thing, like get onto a stage, present my work, set something on fire, pick it up and be like, all right, thank you very much, goodbye. So that's the goal. Biodegradability, it's a bit harder, I guess. So all of the materials are inherently biodegradable, we know this, but it's hard to then prove that the system as a whole, once it's been put together, is still biodegradable. It takes time, and obviously publishing things, you want to try and get it out there as quickly as possible. Maybe do like a high pressure test or something, maybe add some microbes or bacteria and just see if it gets eaten. It would be a nice way to do it as well.
Be careful what you wish for. Pronouncing the words explosion, setting on fire might interest some artists in the back of this room.
We're talking already. It'll happen.
So let's be careful here. Any other question? Yes, thank you.
So, more or less, how long does it take, like, that sheet of mycelium to grow?
2 weeks. So it's quite quick. If you think about like lead times of like, you're there, you've had some ideas, you want to make something, and then you order it online. Maybe a week later it's going to arrive. So 2 weeks you can grow it. It's not too bad.
And can you, like, harvest the spores to, like, keep production, or is this something you have to order?
Yeah, you don't need to. You don't even need to take it to the spore stage, because that actually changes the genetic baseline of the material. Instead, what you do is you just take the mycelium and you just allow it to just keep spreading out as a root structure, and then you just take a piece and it'll want to keep growing. Yeah, life wants to live. It's really cool. So they're actually trying very hard not to allow it to spore, because they've got this material that they know works and has properties that they want. So all they're doing is just letting it just grow and grow. The guy that made it just went into the forest on day one of his PhD, plucked it out of the ground, and that's what he's been working with since, which is so cool. Yeah. One thing to say as well, I was talking, so this presentation is from a meeting I had 2 hours ago. And they were saying that they've actually started exploring this, that NASA's started to explore this for space, because mycelium has really good radioactive negating effects. So like they want to use it for like screens for space. And then now actually they've proven you can grow it in space as well. So if I can find a way to then make some robotic, manipulators, then they already have the ability to make it in space. So it's just like, all right, NASA, here you go. Go make my stuff in space. So that could be cool.
Thank you.
No worries.
Thanks for the presentation, and also, as he said, for showing the evolution. I was wondering, as you were mentioning also these properties, is far-fetched to think about bio-batteries or elements that we can put inside of batteries that we can grow instead of using using the chemical compounds that we use nowadays?
Yeah, a friend of mine actually made a bio-battery that's edible last year. It's ridiculous. It's just.
Can you elaborate on this?
I think it's published. Yeah. It's basically just, so you use carbon powder, which is, we say edible in it, it can go into the body and then leave without causing problems on the way down, right? And then it's within a organic substrate, which then allows the voltage to be generated within it. So it's got a slight capacitance that it will then generate. It's very low. The currents can be super low, the voltage is super low, but it's a battery you can eat, so like, it's progress, which is quite cool. Mycelium as well, because of the thermo properties, it's really good as a substrate for making PCBs, and that's been proven already. So you can actually use it as the backing to then put your electronic components onto. You can use a biological track to then allow electrical charge to flow. So yeah, mycelium is the future.
So there is a company in Brussels that I think has been existing for now a few years, where they make use of, I think, properties of Brussels that are very compatible with mushrooms, humidity. We have a lot of sellers, and so they are actually producing a lot of leather made out of mushrooms, and now the company has been growing. So I think if we were to tell them that we can make robots out of them, I think they would be pretty stoked.
Yeah,
so nice. I will actually do it. So.
Yeah, go for it. Hook us up.
And put you in touch with them.
Please, yeah.
Yeah. Any other question? All right. This was a wonderful way to finish the day. Very inspiring. Thank you so much, Alex. Yeah. And thank you also to all the team behind also organizing this day. Thank you, Anya, Andreas, Luca, and thank you all for coming. Please register, go to brias.be and register to the events. Final words. Thank you.
Cool.